Do a recording of last week's Unit 1 FRQ. I know some of you came into office hours to ask questions, but not all of you, so I just wanted to make sure there was a video of it out there. So we're given this piecewise function n that represents the number of fish in a pond at time t years. It's a piecewise function. And the first part, we're just asked to explain the meaning of the limit as t approaches infinity of n of t. For that, we're going to want to pay attention to the last piece of the function, since we're only concerned with values of t that are large, so definitely greater than 8, right? And so when I take this limit, I'm letting t go to infinity of 200 plus 80t over 2 plus 0.05t. So if we think about the behavior of the numerator and denominator separately, the numerator as t gets large is going to get infinitely large. The denominator is also going to get infinitely large. So we can use L'Hopital's rule since this is an indeterminate form. So remember, L'Hopital's rule tells us take the derivative of the numerator, divide by the derivative of the denominator. Derivative of the denominator is just going to be 0.05, and then try to evaluate the limit again. So this is just a constant. If you throw that in your calculator, 80 divided by 0.05 is 1600. So then it says interpret in the context of the problem, so I'll just say as years go on, the fish population approaches 1600. All right, so let's move on to B. Is the function n continuous at t equals 8? So for n to be continuous, we need the limit as t approaches 8, no, not infinity, 8 of our function n of t to equal n of 8. So we just need to verify that. This limit kind of implies a couple of things. We need the limit as t approaches 8 from the left first. And so if we're approaching 8 from the left, we're going to want to jump to this middle piece of the function because those are numbers on the domain that are smaller than 8 but approaching 8. And so all I'm going to do is substitute 8 directly in for t there. So it's going to be equals 25 times 8 plus 150, which is 350. And now we need to look at the limit as t approaches 8 from the right. And for the overall limit to exist, this has to be the same. But if we're approaching 8 from the right, we're going to want to be looking at this bottom piece again, right? So I'm going to make a direct substitution in for t there. So we're going to have 200 plus 80 times 8 over 2 plus 0.05 times 8, which is also 350. All right, and that's also equal to what n of 8 would be, because that part of the domain is greater than or equal to 8. So now I can just make my final statement, which is going to be the overall limit as t approaches 8 of n of t does equal n of 8, which they're both equal to 350. So yes, n is continuous at t equals 8. Good. Last part, part C. says the function n is continuous at t equals 6. Is there a time for t between 0 and 6 where n of t has to equal 250? All right, so let's look back to here. So they're telling us it's continuous at 6. So it's continuous on that piece, and we also know each separate piece of this is continuous by itself. Therefore, it's going to be continuous for all values between 0 and 6. With that in mind, we can use a little theorem called the intermediate value theorem. So I'll say since f is continuous for all x on the interval 0 to 6, the intermediate value theorem says, oh wait, actually before I do that, I'm going to say and, that's what we want, n of 0 equals f of 0, which is 80. So it's the original population of the fish. And what would n of 6 be? N of 6 that's going to be 25 times 6 plus 150. Which is, what, 300. Okay. So by intermediate value theorem, there exists some time in between 0 and 6 such that n of that time equals 250. And so all we're saying, I'll kind of draw this out visually, right? So all I'm saying is that since we know, all right, so let's say that this is your n, so number of fish, and this is time. We know at time 0, there were 80 fish. We know at time 6, there are, let's say, 300 fish. And we also know that this function is continuous, so there are no breaks in it, right? So at some time, there had to be a time where n of t equals 250, right? Okay, and that's it. This one's just using the intermediate value theorem to justify an answer. Hope this helped.